Okay, welcome to today's lecture. Let me share my slides here. And so last time in Physics 157, we started talking about the effects of mechanical forces on objects combined with the effects of thermal expansion. And so we did a demo with some severe mechanical forces causing changes in the structure of an object, but mostly what we're going to focus on is the situation where we're talking about forces on an object that are causing small changes in lengths, small reversible changes in lengths, and these changes in lengths are just proportional to the forces that we apply. So we had this Young's modulus formula. I don't remember if I said this last time, but if you look at the right-hand side, then delta L is going to be positive if the force is a pulling force. And so we normally associate a positive F in this formula for a pulling force. Okay, that's what we would call a tension force. And we would associate a negative value of F in this formula for a pushing force, or what we would call a compression force. Okay. So this is the basic formula. As long as the change in length is not too large, then we have this linear relationship between the applied force and the change in length. And then the other thing we had was that we can separately have a change in length because of changes in temperature. And today we'll look into some more complicated problems that involve both of these effects, where we have changes in temperature, we have multiple kinds of materials, and then we want to calculate how much force is being produced. Before we start on that, I wanted to have this clicker question where it's just about forces in a static situation. The interesting thing here is that it's talking about a copper wire whose area is changing along the length. Okay, there's a couple of parts to this question. And so the setup is that we have 40 newtons force acting on either end. And we want to know, what is the tension force at various points in the wire? What is the stress at various points in the wire? And just to be clear, what we mean by the tension force is that if we were to imagine considering some particular point on the wire, anywhere you want, and you ask how much force is the right part of the wire pulling on the left part of the wire at that point, that's the tension force. Or equivalently, by Newton's third law, how much force is the left part of the wire pulling on the right part of the wire? Okay. So read through this question and pause the video, think about it a little bit, and then we'll answer the question. Okay, so I'm going to answer the question. Let's draw a picture to start out with where we have our wire. We have our 40 newtons on one end. We have our 40 newtons on the other end. And I want to start by just going from the definition of tension. So let's think about dividing the wire at some arbitrary point along the wire. And the tension force was the force with which the right part of the wire is pulling on the left part of the wire. So I'll call that F tension. So what is that force? Well, a way to understand it is to look at the net force on that part of the wire. Because it's an equilibrium situation, it's a static situation, we can say that the part of the wire on the left is not accelerating. And so what we know is that the net force is equal to 0 because A is equal to 0. So Newton's second law says that the net force on that part of the wire is equal to 0. Now we know that there's 40 newtons pulling on the left, and so it must be that F tension is also equal to 40 newtons. that applies for any point along the wire that we choose. And so we can say that the tension on the wire is a constant 40 newtons. What about the stress? So the stress is defined to be the force divided by the cross-sectional area. The cross-sectional area varies along the wire, and so the stress is going to be larger where you have a smaller cross-sectional area and smaller where you have a larger cross-sectional area. And this makes sense because if you are pulling on this wire, remember the stress is the thing that is ultimately proportional to the stretching of the wire, to this change in length. And we would expect that if I exerted the same force, if I had the same tension at all these points in the wire, then the places where the wire is thinner are going to stretch out more. They're going to have more strain, and that's because the stress, the force divided by the area, is greater for those thinner parts. The parts that are thicker are not going to be affected as much by this force. Even though it's the same tension force, the stress is less once you divide by that cross-sectional area. Okay, so let's get into an interesting problem involving thermal expansion and calculating the forces due to thermal expansion. So we did a problem like that last time, the one indicated in this diagram, where we have an object that's between two rigid walls, and we said that as you heat up the object, if it's prevented from expanding, then there will be forces generated. And we understood that the way to calculate those forces was first to calculate how much does the object expand due to thermal expansion, and then figure out how much force do we need to exert in order to reverse that expansion. We ended up with a formula for the force in terms of the Young's modulus and alpha and the change in temperature. And I want just to emphasize that that's a formula that applies to this specific situation where the object has no change in length. The textbook indicates it as some general formula for thermal stress, but you have to be very careful because that formula really only applies in the case where there's zero net change in length. So my advice is actually to ignore the formula in the textbook. We were able to derive it easily last time just by the idea that you have one change in length due to thermal expansion and then a compensating change in length due to the forces. Today we'll see examples where that specific formula is not going to apply, but we can still solve the problem just using our thermal expansion formula, which is indicated here, and our Young's modulus formula, which is indicated here. Okay. So the problem that we're going to tackle is going to involve multiple parts in a system. And these parts are exerting forces on each other, and they're all undergoing thermal expansion. And so it's quite complicated on the surface. But what I want to emphasize is the problem-solving strategy that I mentioned in a previous lecture. In complicated situations, it's useful to focus on the individual parts first, understand what's happening to those individual parts, and then understand how the parts are related. And so this question has to do with the individual parts of a system. The most complicated thing that's going to happen to some part of a system in these thermal stress problems is that there may be a change in temperature and there may be a change in the amount of applied force. So that's indicated here in this before and after picture. And the thing that we'll want to predict often is how much is the length going to change. So what is this delta L going from the first situation to the second situation under the change in temperature and the change in force? So I'll give you some time to think about that. Pause the video, see if you can work it out. And now I'll tell you how to think through this. Okay, so let's look at our situation. we have, I think I'll just turn this off to get clearer. So we have the force acting originally, and we have some original temperature, and then we have a change in temperature, and we have a change in force. And we want to know delta L. So the hint says that we're able to consider separately the effects of a changing temperature and the effects of a changing force. And so it's easy to write down the temperature change. That's just the thermal expansion formula. We can write that as delta L thermal equals alpha times L0 times delta T. What about the change in length due to the extra force that we're applying? So we have this formula, F over A equals Y delta L over L. And we can rearrange that to give the following, that delta L is equal to L over AY, L0 over AY times F. So this is almost what we need, but not quite. So this formula has a force which is the total force that's being applied. And this tells me the total change in length relative to the situation with no force. What we want in this question is the change in length that happens after I add an additional force to the wire. So it's not hard to see that that additional change in length, I'll say delta L extra, is basically just given by the same formula, but instead of F, we put the change in force. So let me motivate that by a picture. So let's say this axis is the force, and this action is the change in length, the total change in length that we would get compared to the length when there is no force. And our equation says that this is a straight line. So if we apply some force, then we get some change in length. But it's a very simple proportional relationship. And so what you see is that if I now were to apply an additional force, let's say it's the same as the original force, then we're going to get the same change in length as before. The additional change in length is governed by the same formula as for the original change in length. So in other words, when we have this relation, the expression in brackets, that's like the slope of that line. And so if I have an additional change in force, I can just multiply that by the slope to get the additional change in length. Okay. So our answer then is that we have a change in length due to the thermal expansion, a change in length due to this change in force, and then we just add those things up. Okay, so here that is again. Here's our formula for the total expansion. So I want to emphasize how useful this formula is going to be for you. It applies in pretty much any situation where it could be a very complicated situation with 400 different parts in a structure, but you can always look at those individual parts. And when we're dealing with thermal expansion problems, the only thing that's generally happening to the individual parts of your system would be changes in temperature and changes in the applied forces. And so this formula is what you are going to need to relate those things to the change in length. Okay. So it's really important to remember the change in length. Oh, sorry, I'm going to move this back so I'm not talking to blank screen. The change in length total is the change in length due to the thermal expansion plus the change in length due to the changing forces. So we are now ready, equipped with that, we are now ready to tackle this more challenging problem. This is actually one of the most challenging kinds of problems that you're going to see in Physics 157, but it's really not bad at all once you break it down logically and follow my strategy of understanding what happens to the individual parts and then understanding how these parts are related. So let's have a read through the problem. And step one, or maybe step zero, if you're dealing with a problem like this, it's just to visualize what the question is telling you. This is very important. Take the time to understand what exactly is happening in the question. And I would recommend actually drawing a picture in order to help you visualize. So draw a before picture and an after picture and understand what's changing and label the quantities that you know and that you don't know. Once you have that on paper, it helps us process the information and understand how to tackle the question. Okay. So let me start doing that here. Okay, so the before picture is very simple. It describes a situation where two rods of equal length but different material are stretched between rigid walls and the temperature is 20 degrees Celsius. What about the after picture? So before we start that, I have a quick question for you. This has to do with visualizing what's going to happen and what the question is telling you. So as we have this change in temperature, what's going to happen? Are both rods going to increase in length? Will they both stay the same length? Will one get longer and the other get shorter? In that case, does the total length stay the same or does the total length change? So take a minute to think about it. And now we'll talk about the answer. So the situation in the question says that there are rigid walls on either side. What that means is that the total distance between these two walls does not change. The total distance is the sum of the lengths of the rods. And so we could be sure that whatever happens in the question, the sum of the lengths of the two rods is going to remain the same. But because the rods are made of different materials with different properties, we don't know that both rods are going to remain the same length. In fact, it's unlikely that, because it's not a symmetrical situation, it's unlikely that both rods will behave in exactly the same way. And so what we would expect generically is that one rod is going to get larger and the other rod is going to end up shrinking. Okay. And that could be because this one rod has a larger thermal expansion coefficient. It wants to expand more, but it's also depending on the Young's modulus. If one of the materials is extremely stiff, then it's less likely to be compressed. Okay, so the answer was that one rod will get longer, the other will get shorter, but the total lengths will remain the same. Okay, and so with that in mind, I can draw an after picture. So what I've drawn is this rod getting a little bit longer, this rod getting a little bit shorter, and I'm indicating that by saying that the length of this rod afterwards is L plus delta L1. The length of this one afterwards is L plus delta L2. And we have this constraint that the total length is fixed. Okay. So this is part of the relating the two parts. That was one of my strategies. The second strategy was to understand how the various parts are related. So this relation delta L1 plus delta L2 equals 0 is an equation that relates quantities that govern the individual parts. So that's what's going on. We have these possible changes in length due to the change in temperature. And the other important thing that we're going to have to think about are the forces that are generated. So the question asks about a force on the wall from the rods. And so I've indicated that there and labeled this unknown quantity F. There are also forces from the wall on the rod and on the rod from the other rod. So I could also indicate those on the diagram, and I'll do that in the next slide. Okay, so this was our setup. This is just understanding the problem, drawing the picture, defining variables for our unknowns, and using the broad discussion of the question to understand if there are some relationships between these unknowns. Now I want to go to the part where we focus on the individual parts of the system. And to help me do that, what I'm actually going to do is draw a specific diagram before and after for each part. Now, you don't always have to do that, but I'm doing it just to make it completely clear what's going on. So let's look at the left part. We originally have a rod with length L and temperature T, 0 forces. Now we change the temperature. We're going to get compressive, some forces that could be generated on either side, and we might have a change in length. Same thing with the second rod. And so this is basically, if you look at each of these parts, it's basically the situation that we already discussed. Okay. There's one thing here that will be helpful to us, which is that these forces, even though I've drawn them as being F1, F2, F3, F4, we can relate them all by thinking about Newton's laws. Okay. So this is, again, I guess, a part of the question where we're understanding how quantities in different parts of the system are related to each other. So I want you to think about that for a couple of minutes. Understand, if I look at this force, this force, this force, and this force, how are those related to each other and to these forces with which the rods are pushing on the walls? And see if you can come up with a specific argument for why what you think is right is actually the right answer. Can you come up with an argument based on Newton's laws? Okay, so let's have a look at the situation. We've drawn all of the forces from the diagrams above onto the single picture below. And so this is actually a lot like the first clicker question that we did in today's class. So it's going to be a very similar argument. And we're going to argue that all the forces everywhere in this situation are actually the same. So it's a combination of two things. Newton's third law tells us that if one object is pushing on another one, then the other object is pushing back with exactly the same magnitude of force. So Newton's third law tells us that F1, the force of the wall on the rod, is equal to the force of the rod on the wall. So F1 equals F. Newton's third law also tells us that F2 equals F3. The force of the left rod on the right rod is equal to the force of the right rod on the left rod in magnitude. And it tells us that F4 is equal to F. Next, we need to use Newton's second law to say that F1 equals F2 and F3 equals F4. And this is exactly the argument that we gave before. We know that the left side of the rod is not accelerating. Therefore, it must have 0 net force. And therefore, F1 in magnitude is equal to F2 in magnitude. And similarly, F3 is equal to F4. So we probably, in doing this question, could have skipped the step, and it might have been intuitively obvious to us that all of these forces have to be the same. Otherwise, the system would not be balanced, and it would not be in equilibrium. But I wanted to do that in detail just so that you could understand the logic. So you might have just jumped right to this picture here, and that would have been fine. Maybe you would note in your solution that this is true because the system is in mechanical equilibrium. So now we are basically ready to finish the question. And so what I said was that we want to understand how each part of the system is changing. So now we've isolated the two parts, we've drawn our pictures, and we realize that it is exactly the same as the problem that we talked about earlier, except we have a pushing force instead of a pulling force. So we have a changing temperature and a changing force. And so we can write down the equation that gives the change in length of the first part in terms of that change in temperature and in terms of that new force. Here we have originally force equals 0, and so this F that we're generating is also equal to the change in force. So we have this equation, and it's very similar to the one we had before, except for the minus sign. The minus sign is there because we've got a pushing force instead of a pulling force. And so you're just going to use your intuition here. If I've drawn the picture and I have a pushing force, that's clearly going to cause a decrease in the length. If that were the only, so just the change in length because of that is negative. So we have these minus signs here. If we happen to have a situation where it was a pulling force, maybe it was a cooling situation where you generate tension, then you're going to have a force that's pointing in the other direction, and then you would write a plus sign like we did in the previous question. Okay. So we have an equation that tells us how much the length of the first object is changing. We have an equation that tells us how much the length of the second object is changing. The only thing in this equation that we don't know is F. Everything else we know. And so if we take this pair of equations and then combine it with our earlier result that delta L1 plus delta L2 is equal to 0, then we'll be able to solve the problem. Okay. So you see that if I plug in the second expression for delta L1 and the third expression for delta L2, then we have one equation with one unknown, F, and we can solve for that easily. So I'll do that at the beginning of next class, but you can try it on your own in the meantime and plug in the numbers from the question to see how big this force that's generated is. Okay. So just a final summary, I want to emphasize the general approach we took. We visualized, we drew our pictures, we understood what the unknown variables were, labeled them on the diagram. Then we looked at the individual parts of the system and we wrote down an equation for each part that told us how that part was changing, how the length of that part was changing. And then we understood how the various parts were related. So we had this formula that related the change in lengths, and that was from the question, just understanding what it was telling us in the question. And then we also had some discussion about how the forces acting on the various parts of the system were related, and that was using Newton's laws. All right, so we'll see you next time.